Um, last review, okay, guys? This is our final push. Last review. I want you to do this multiple choice today. We'll go over that and some final things tomorrow, and then karaoke. So here we go. On page 143, this is the last section, chi-squared and test linear regression t-test. We did those most recently. We did those in the 5th 6 weeks, so we won't do much review here. So first thing to state, chi-squared are tests when you're dealing with multiple proportions. Okay? Chi-squareds are tests for multiple proportions. Linear regression t-tests are your tests that you're going to test for a relationship, a linear relationship. So you're testing for the slope of the relationship between things. All right? So on the next page, it goes through a review of the chi-squared. Remember, there are 3 different kinds of chi-squareds: the goodness of fit, the homogeneity, and the independence. So here's a quick review. Goodness of fit. Goodness of fit is the ones where there is only one group. Only one group. And then you have claimed percentages for those groups. Claimed percentages. The degrees of freedom, such as regular M&Ms is one group, and the claimed percentages for their colors. You know, they say what color there should be, percent there should be for each color coming off the assembly line. So you put your observed data into list 1, and you put your expected counts, turn them into counts, into list 2. Remember, percent times the total will be how many counts you expect. Your degrees of freedom is categories minus 1. So if it's 5 colors, degrees of freedom would be 4, because it would be colors minus 1. All right, chi-squared test of independence. Independence has 2 or more groups, such as regular, peanut, and peanut butter M&Ms. See? 3 groups, but only one category, brown or not brown. Okay? Regular, peanut, peanut butter, and then brown or not brown. You will have to then, remember, these ones we go put in our matrix, not in the lists. And the degrees of freedom is rows minus 1 times categories minus 1. The matrix ones have the rows minus 1 times categories minus 1. All right? And then the chi-squared test of independence is 2 totally separate variables. So, for example, the types of M&Ms and the color, the whole spectrum of the colors. So the type of M&Ms, regular, peanut, peanut butter, and then the whole spectrum of colors, not just brown, not brown, but brown, blue, red, yellow, so on. Again, these also use the matrix, and it's rows minus 1 times categories minus 1 for degrees of freedom as well. Now, conditions. Conditions are still random, independent, large enough. So same random, independent stuff, but let's talk large enough. For our large enough, let's do a quick review. Our large enough for means is what? N is greater than or equal to 30. Our large enough for proportions are what? NP and N times 1 minus P are both greater than or equal to 10. But our large enough for chi-squareds are that the expected counts are greater than or equal to 5. And you need to show these. So that's show your expected matrix or show your expected counts in your list. Write them out and say, see person, I know that this is what I got to look for, and all of these expected counts are greater than or equal to 5. Yes. See nice person who's taking a week off in their summer to come and grade all these tests? Okay? It's probably equal to also, yeah. I doubt there's going to be one that's just like right on there, and it's like you're like, okay, which way do I go? All right. So now, if you have to do the expected by hand, remember that? It's for each little cell, you know, you can do that. Remember, row total times column total over total total. You might. Row total times, not for the whole thing, but maybe if they ask you just for one cell. Okay? And if they say, hey, what contributed most to the deal? Do you remember standardized residuals? Here is that little observed minus expected over square root of expected. So all of those things are not on the formula chart. Okay, questions? What? That said residuals. So I put a D in there. So it's not a typo. Residuals. Okay, now, linear regression t-test. About all I want to point out on this for you is let's review our conditions. Remember, these ones are pretty crazy, but you're going to if you have to do this as a free response, they will most likely give you the graphs. We're just going with that they're going to give you the graphs. So remember, for linearity, you are going to tell the R value, and then you're going to also check the one that shows a graph like that. For independent, randomly, those you know how to do, those you state the same way. Normal probability plot. This one is going to look this graph will look one of two ways. You are saying that the residuals are fairly normally distributed. That's what you are saying for the N part of our conditions. And our pictures will look probably, remember this thing where it's like that, where it's like a little bit more condensed in the middle? And these are, so, or it may give you a histogram of the residuals. And so if it's giving you a histogram of the residuals, remember, there's more residuals in the middle where the z-scores are 0. Okay. And then the last one, equal variance in the residual plot. So that's where you say the residuals are equally scattered on either side of LSRL. And that looks like this one, where you don't want it to fan out. No fanning out. Okay. And then last thing that's not on the formula chart that degrees of freedom are n minus 2, because it's two variables. Degrees of freedom n minus 2. And what happens if they ask you to give the standard deviation of the slope? Remember, standard deviation of the slope is b over t. It's a pain in the butt. Standard deviation of the slope is a pain in the butt. Okay? All right. So your homework, final homework of the year, is pages 146 to 154. Okay? Last thing, 146 to 154.